Good
Hi,
evening, am I audible, sir?
yeah, I can hear you. Can you hear me?
Yes, sir, you're audible, sir. So, good evening, everyone. Thank you once again for joining us. Welcome you all to the second guest talk of STATIFY 2.0, the month-long Gen AI bootcamp organized by FIBS IIT Bhubaneswar. To begin this session, I would like to give a brief introduction of our guest speaker for the evening, Mr. Sabyasachi Parida. Sir is a data scientist with expertise in building scalable machine learning and deep learning models to solve complex challenges. He is currently working as a senior applied AI scientist at Best Buy. He has been a mentor guiding students on data science projects and a lecturer at various educational institutions on advanced data science topics. Thank you so much for joining us today, sir. Over to you.
Thank you so much, Sriram, for the lovely introduction. And yeah, it's a privilege to be here once again. I think after 2 years with FEBS for IT Bhubaneswar and also for presenting to the lovely audience, as usual, who are quite receptive of what I present generally and taking it as a matter of pride. Thanks for the invite once again. And I will be presenting this time on the emerging topics of Gen AI, which is on the RAGs. Starting from RAG, we will go to the next of how uh, does RAG work, and let's then diverge into the agentic framework as how we can build agents using the LLMs, and touching base on the components of the lang graph as how we can use lang graph to build systems on top of the uh, lang graph components, and then we will touch some of the components of lang graph, and then we will see as how the multi-agent structure is working. It will be much more not like too deep into each of the components, but rather speaking about what are the different components rather theoretically, and giving some insights into some of the codes which are available open source as well from LangGraph and LangChain as well. So, and if any of the students have got any of the doubt in any of the time, just feel free to ask that on the chat. I like, if you can access the chat, then it's well and good. Otherwise, like, if the host can also let me know, then that can also be fine as well. Or otherwise, post this call, I can also be available to take up some of the calls, say offline as well. Okay, I'll be sharing my screen. Just give me a.
Hello, excuse me, sir.
Yeah.
Sir, can we wait for 5 more minutes? We are waiting for people to join the stream.
Okay. Okay. Sure. 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 I can be online,
Yeah, sir. You can be on.
and my screen is visible, right?
Yes, sir.
Okay.
Thank you, sir, for waiting. We can start now.
Okay, yeah. Let me share my screen. Uh, Hopefully I'm audible and my screen is visible as well. Yeah, okay. So without wasting much time, so let's start as I discussed in the introduction as well. So for the students or for the people who have joined late into the session, so today we will be covering some of the important. What has happened? Yeah, so today we will be. My screen is visible, right? Can the host confirm?
Yes, sir, screen is visible.
Okay. Yeah. Yeah. So for the audience like who joined late, so today we will be covering the session starting from the uh, topic of RAG as how the RAG works, and then we will be taking up into the next sequential part of the things like how semantic routing works, how does the particular system knows that what is the intent of the particular message, whether it needs to call a tool or whether it needs to call an LLM or whether it needs to call a RAG in itself as well. And then we will be covering some of the aspects of the lang graph as what is the lang graph and how what was the need of the lang graph and how it had evolved from the lang chain. And then some of the components of the lang graph as like what are the different components, like how does it incorporate memory as and how does it incorporates conditions into it like the control flow and some of the important aspects of say debugging and also knowing as how uh, line graph is crash proof as such, like with the user persistence and time travel as such. And then also touching some of the components of how multi-agent system can be built using the line graph, which are also like most of the things is what you see indirectly in some of the applications of the chat GPT or the open, like say the Claude frameworks as such. Okay, so let's start with the RAG. Okay, so RAG, as the name suggests, is nothing but the retrieval augmented generation. So it has got three parts. One is the retrieval, the second is the augmented. Retrieval is like retrieving something, okay, and A is augmenting. Augmenting means adding something on top of something what we have. And with the inclusion of both retrieval and augmentation, we are doing a generation at the end. So RAG, if we know, like as we know that LLMs, like any of the open LLM model, let's take say the OpenAI or say the DeepSeek or say the Claude, right? Any of the LLM models which are there, they have like a fixed training cutoff date. Like if you remember, like the GPT when it came initially, it had a fixed training cutoff date, like say for 2023 or 2024, right? Apart from that, like beyond that, if we ask anything, the particular chat gpt as such at that point of time was also unable to answer the questions which were beyond that, like what is say if we ask say the LLM cutoff date is say 2023, and if we ask something which has happened beyond 2023, the LLM, like say Trump has won the US elections post certain date, and if we ask the LLM which was trained beyond the certain date, it won't know and it would give as the correct like the answer to be the prior president of the US. So these all kind of a things were like specific to the LLM, that what it had been trained and what all scenarios it had known, it would just predict the knowledge based on that. Because like LLMs, if you know, like these are nothing but like the next uh, token or the next sentence or the next keyword prediction kind of a system. They don't know like what is the context of that or what is the intuition behind that as such. Okay, so these were one of some of the major problems which were happening in the LLMs. Like they have a fixed cutoff for the training, and they can't access the proprietary or the private data. Suppose say I have a specific leave policy or a specific HR policy in my system in my organization. I want my LLM to know as what are the things and be grounded. That means if I ask some questions like how many sick leaves I have in a year, or say if I ask a specific question that what is the when is the next leave coming, or what is the exit policy in my system, then the LLM would give answer which is generic to the whole world, because the data on which it is trained, like all of the Wikipedia, all the Reddit knowledge, And everything on which it has trained, it knows a generic knowledge. It doesn't know what is specific to my organization. If I want it to be known specific, then I have to have some kind of a different approach. Okay. And the other thing is, like, if I want the particular LLM to know that for my organization this is the leave policy and these are the HR documents, then what the one way which I can do is like to retrain the particular LLM model. Okay. But LLMs are quite expensive to train. There are, say, some of the models are like 7 billion parameters or like more than that. Training such a huge model generally takes months and huge months, and also quite expensive in terms of the GPUs and the hardware components that we need. I don't have that much liberty to retrain a particular model based on whatever the specific information that I have. So there comes the RAG, which is the retrieval augmented generation. In this, what I do is that I retrieve the relevant chunks at the query time and inject a context into the prompt. So based on the context, whatever I have, I just ingest that into the prompt. And with that, I just mitigate the scope of like no retraining. That means there is no retraining which is required, and also that it needs to be grounded. That means whatever answer it is giving, it needs to be grounded with respect to the whatever data I have provided. It should not be hallucinating or going above or beyond that. So the rack pipeline, if you see, it has got multiple components in it. So first we need to load the particular document, whatever is there. And for loading the document, we can't just directly load every document into it. Okay, so there needs to be some kind of a splitting strategy. That means how we need to split the particular document. And obviously, like these are texts, we need to create some kind of embedding so that the model or the particular system is able to learn. Okay, that means the embedding needs to be there. And after doing the embedding, we need to store it somewhere, like some kind of a database wherein we can store all of our systems over there. And the fifth is a retrieval, like how we want to retrieve the particular documents. And the last is a generate. As with the retrieved document, how can I generate my output which is grounded on the knowledge whatever is there. Okay. So and so like let's go like first we will cover these three parts, like the loading, the splitting, and the embedding, and the next part we will be covering the storing, retrieving, and the generation part. So there are various different types of document loaders which are available. Suppose I have got a text file .txt file, then I can use the text loader. So in LangChain, if you see in the documentation, these are already available for you. The text loader, the PyPDF loader, the web-based loader. Like if I want to do a web scraping, then I can use the web-based loader. I can directly just pass the URL of the particular web page, and with that, it can directly extract the contents out of it. And like the CSV loader, suppose I have got multiple CSV files, like the Excel files which you understand, multiple CSV files, then I can use a CSV loader. So what it does is that the document loader, it generally what it does is it just creates a loader object which on the set of document whatever I have, suppose I have got the PDF documents, okay, some 10 PDF documents, it just creates a loader object and creates the document. It just creates a loader object out of it. And there is something called as a load versus lazy load. Suppose I have got 1000 GB of data, right? Or say more than say 500 GB of data. I don't want my system to halt at that point of time. So what I can do is the lazy load. That means I can it can run my command at that point of time, but with the scope of the lazy load, what it does is that it can avoid the memory spikes. That means it will do a batch wise load and it will not be inline during the code execution. After loading the document, the next thing which comes is the text splitting. So suppose say I have got a say what 10,000 line documents. Okay, I want my model to not my model, my RAG system to know it. So there are the three parameters which essentially are the part in the lang chain. So one is the chunk size, the other is the chunk overlap. So chunk size is what is the maximum characters per chunk. So chunk, if we would understand, suppose I have got 1,000 document, I want to break it into multiple chunks. So one chunk would be, suppose I define the maximum chunk size to be 200. So the individual chunks would be of 200 characters each. Okay. And there is something called as chunk overlap. Suppose say I want, because like if you read some paragraph, you might understand that the second paragraph would be somewhere related to the first paragraph, right? And the third paragraph would somewhere related to the second paragraph. So what I want the uh, RAG system to know is that there is an overlap between the multiple chunks which are there. So there is a chunk overlap. So from the first paragraph, yes. So from the first paragraph, from the 200 documents, suppose I have made the chunk overlap to be say 10. Okay. So 200 characters from the first paragraph would be picked up, and 200 and then if the chunk overlap is 10, so 10 characters from the first paragraph and then 190 characters from the second paragraph would be picked up. Okay. And there are different kind of text splitting what I can do. Suppose say I want to break the uh, make the chunks based on the default page break, which is the slash n. Okay. So that is by using the character text splitter. It by default uses the page break as the uh, default mode to create the chunks. And there is something called as a recursive character text splitter, in which I can define multiple different type of separators to create the chunks. So one can be the slash n, which is the page break, and there is something called as a tab. If it sees a tab, it knows that this is something, there is a page break or something different which is happening, and then it can create a new chunk from the consecutive after the tab which is coming. Okay, so this is generally used in most of the purposes, and it also solves most of the tasks as well. And there is something called as a semantic chunker and the markdown header text splitter. So semantic chunker is something like I want to understand that suppose say there is semantic meaning out of it. I don't want to make it typically say 200 characters in the first line versus 200 characters in the second line as such. I want there should be semantic meaning. Okay, so in this I can use something like a cosine similarity, which we will come later as well. And based on the semantic meaning, based on the meaning of the different chunks, it breaks down the different uh, it creates the different chunks as well. And then after creating the chunks, like first I have loaded the document. If you would see, there is load of the document and split, and there is the embedding. So after this, I need to create the embeddings. So for creation of the embeddings, which is nothing but like for whatever paragraphs I have, I want it to convert into some kind of a meaningful vectors so that my model understands and it can also extract those things. So embeddings is nothing but turning text into vectors. Okay. So there are two parts which are there. One is the embed documents and the other is the embed query. So embed documents is used for while creating the corpus, whatever I have. For say the PDF, whatever I was saying, there are a 1,000 line PDFs and it had created all of the chunks. For every chunk, we need to embed it. Okay, so suppose say the first 200 characters which are there, that needs to be from text into vectors. It would create like from the set of characters to a list and list of float. Okay, so there are different kind of embeddings which are available. So the most commons which are there, like the OpenAI embedding, like the text embedding 3 small, text embedding 3 large. Okay, and like all mini LM L6v2, like if you have used a sentence transformer, this is something which is the most commonly used. So with this I am converting the text. Suppose that there is a text like the king is in the castle, right? So king and castle both are semantically similar. Okay, the king is in the castle, the queen is also there, right? The king, castle, and the queen, those are semantically similar. And based on the embedding model, because it has trained on multiple different corpus of Wikipedia, Reddit, and all those things, it knows what is the semantic meaning between those, and it would give a vector value to each of the text. I think all of you must be aware of this, so just a like a revision into that. So that like the king would be, suppose it gives gets a vector of say 1, and the queen gets a vector of 3 and the castle gets a vector of 2. So king and the castle are mostly semantically similar to each other, and also queen is also similar to each other. And there is something called as a dog is there or a cat is there, right? Cat and king, those are not semantically similar. So in the vector space, those would be quite separate from each other. So that is taken care by the text embeddings, which is what we use while creating the embeddings from the loaded text splitted documents. Okay. Okay, then we can come to the next part. Say like we have created the embeddings, like how to use those embeddings. Okay, like for all of the corpus of the documents, whatever I have created, I need to use it in a certain way so that like while I am asking something like what is my specific, how many sick leaves are there, or what is when is the next holiday coming, it needs to know like based on the query whatever I'm asking, what is the exact meaning of that, and also based on the documents whatever I have ingested into the system, it can extract or retrieve the relevant chunks rather than retrieving any of the other chunks. Okay, so there are the different kind of vector stores which are there because I want it to be fast. Like you can say that why not to save it locally, right? Locally, like in say an Excel file or a CSV file, I can store it, but the issue over there is that like the retrieval is quite tedious. It might not be fast as I expect. So there comes the some of the important components like the ChromaDB, the files, the Pinecone. These are all the different databases wherein I can store it, and also they have got their individual algorithms embedded as such, wherein they can extract the particular say the query or the relevant information using the proprietary algorithm. Okay, so the mostly the ones which are used are the ChromaDB or the files, and a brief into that is I'll pass on this slide anyways, so you can know more about like what does FIS use or what does say the uh, ChromaDB uses, like the ANN, artificial neural network, sorry, approximate nearest neighbor, or say the IVF, which is inverted file index, which is similar to the K-means clustering as well. So the retrieval is something which is of the most concern. Like suppose you are asking what is the leave policy in my organization, and you don't want to wait say like another 5 to 10 minutes more, because it would go into the system and then it would retrieve the set of relevant documents, and then it will do a nearest neighbor search and get and then it would pass on to the LLM and then it would give you the answer, right? You want it to be faster. So for that, we use these all kind of systems like the ChromaDB, FIS, Pinecone, all those things. And the way the retrieval works is that like suppose say I want the most relevant things to be available, then I can use like some of the uh, available retrieval strategies like the BM25, which is like the TF-IDF only, but it is much more better as compared to the TF-IDF, which is the term frequency and the inverse document frequency. And there is something called as a maximal MMR, which is the maximal marginal relevance. Suppose I want to retrieve the documents. Suppose I want to know like what is the leave policy in my organization. Therein it would retrieve say the set of documents which are relevant to the leave policy, as well as like if it wants to know like because of the there is something which is something specific to say different grades or different bands, the leave policy are separate, so it can also retrieve those chunks as well. So therein I want much more diversity over there rather than picking up those specific exact documents. Okay, there in those cases, the ensemble retriever or the hybrid search, they mostly play a greater role over there. And there we use something called as a reciprocal rank fusion. Okay, and so all of this is included in the LangChain. So like you don't have to do most of the things, and also this is also included, say in how whether you use the ChromaDB or the Pinecone or those. There is something called as a parameter called as a similarity search with score. So here you just pass like what is the kind of a similarity you are expecting, like the MMR for the maximal marginal relevance search, or like similarity search, it would just do a cosine similarity, and it would like k equal to 4. Then it would retrieve the top 4 relevant documents. Okay, so we have stored the data. We have, first what we have done, we have loaded the PDF, we have splitted those PDF, and then what we have done, then we have yeah, first we have loaded those PDF, we have splitted those PDF, and then we have made those into meaningful embeddings, and then we have stored it into a vector store, right? And then the next part, what we are doing is the retrieval, and then comes the generation. Okay, so let's see how the retrieval works. So for the retrieval, as I was saying, like one of the most common way is like, so there are two retrieval which are happening. One is on the uh, uh, for the set of query whatever I'm passing, it does a similarity search, and it also extracts what are the relevant set of chunks which are there. Okay, so uh, there are different kind of a retrieval patterns which are there, like as I already said, there is ensemble retriever, and also there is a contextual compression retriever or parent document retriever, wherein parent document retriever is something, what I would say is that, suppose there is a big so there are 3 4 paragraphs which are there, and I have broken down it into, based on the token or the based on the splitting strategy, 200 200 200 each. But I want one to be a parent, so the parent would be say the one page, and within that the 4 or the 5 individual chunks will be the child. Okay, so this kind of a retrieval it is also there. So depending upon your use case, like suppose there is a hierarchical uh, relevancy within each, or there is some kind of a specific application wherein I need that there would be a relation between that, or there would be semantic meaning between that, or I need maximum diversity within that, then based on that you can use any of the retrieval strategies. Okay, so the most commonly like use is the ensemble retriever, wherein like we use the available set of top k, where we give a equal weightage, like a diversity weightage, like the top k documents need to be extracted, as well as to on top of it another say 4 or 5 to which are semantically similar, and also like those are also not too far from the original query whatever I'm asking. Okay, and with this I have built up the RAG module in the LangChain, and this is say one of the component which is there in the system. So whenever I need, suppose say I want to call an LLM, and the LLM is there, and I want to ask like what is the leave policy. So in that case, how will my LLM model know that I am asking the leave policy, whether that is relevant from my organization, or whether that is needed from the external knowledge whatever it has, right? Or suppose say I ask how is the weather of Bangalore today, then in that case how will it know like whether that needs to be called from a RAG system, or that needs to be generated out of its own knowledge, or it needs to call an external say weather API. Okay, in that case there is something called as semantic routing, wherein we want the particular LLM model, because LLM is nothing at the end of the day, it's just a text prediction system. It would predict the next sentence only. It doesn't know, it has got no memory, it has got no knowledge in itself to take up any call or take up any of the actions on its own. So we have to inherently or explicitly define it so that the LLM can have a brain on its own. Okay, so if the particular LLM model knows, or the particular framework whatever we are building, so LangChain and LangGraph are nothing but frameworks. These are frameworks what we are building to infuse or to help the model to perform as per our expectations. Okay, so there are different kind of a like way or the techniques through which we can do the semantic routing. So one is the embedding, similarity. Like here, we don't have to have any of the other LLM call. It just based on the embedding. Suppose say I have already embedded my documents, right? And similarly, I have embedded the query as well. So suppose say the query is how is the weather today, and then as per the embedding using say the all mini LM L6V2, the sentence transformer embedding, it knows that the embedding corresponds to some kind of a weather information, right? In that case, it doesn't need to do any of the LLM call. It just directly would uh, call, say, the available tool which is there, or suppose in the case of a LangChain where the tool is also not available, then it also can do a direct routing as such. Okay, or suppose say there is what is the leave policy of my organization, then it does a embedding similarity, and because the similarity is similar to whatever is there in the rag documents, it would just retrieve those documents and give the answer. Okay, one is through the embedding similarity and the other is through the LLM classification. That means I have the LLM explicitly there, and the LLM would, based on the query whatever I'm passing, it would just give you a label at the end of the day, that this label, like suppose how is the weather today, it would directly give us that this is a tool call, or what is the HR policy, or what is the leave policy in my organization, and then it would give a directly label as a what a rag call, okay, rather than an LLM call. And the most interesting part, which is there obviously for us, is the line graph conditional edges, right? Without using all those things, like through the use of line graph, I will also cover this during the different components of the line graph as how we can use the conditional edges. So over there, using the conditional edges, we can directly explicitly know our line graph framework know that there is a state which is available, and there is a node which is available which can do the say the API call, and there is a node which is available which can do the RAG based call as such. And based on the conditions, it would just direct into that particular direction in itself, which was unavailable in the LangChain previously. Okay. Okay, so let's start with the basics of the Lang graph. Let me just see like if there are any questions or others. I don't think there are any questions in the chat. I think I don't think there are any. Yeah, so there aren't any questions currently. So if there are any questions, just write it in the comment box. I will take it up as we progress through the session. Okay. Yeah, so let's see. Oh, like I think in the last week you had another talk which was on the LangChain, and you had like you I think you would have covered some of the components of the LangChain and how to use the LangChain and everything. So today in this call we will cover the basics of the line graph as what is the different components of the line graph. We will not go too deep into the other advanced stuffs. I will just give you some of the highlights of what are the different extra components which are available, and a basic deep down analysis of as what why do we need each of the components as, and what does each of the component serve in itself. Okay. Okay, so for the Lang graph, so as the name suggests, so Lang graph is the Lang. There is a component called as a graph. Okay, so it's a graph-based data structure wherein we are uplifting the graph-based data structure to achieve our task. Okay, and one of the main component which is there in the Lang graph is the state. So unlike in LangChain, where we don't have a state as such, in the Lang graph we have the state component. So the state component is something which is like the main definition of the Lang graph. That means each and everything happens around the state of the Lang graph. Okay. So every node, like if you visualize any of the graph, like there would be nodes which are there, and also for every node would be connected to each other or to any other through the edges. Okay, so like a state is something, is a type dict defining the shared data structure. So the data type of a state is always a dict, and we have kept it to be type dict so that we don't have to face any of the errors during execution. So the data type would be always be type dict. And by definition, like suppose say like this is a dictionary, and the dictionary I want something like a messages is one, say the key, and the key is of a dictionary, and it can take a list of messages. Okay, and the annotated is something like, I would suggest you to go through this separately, the type ticked, the annotated, the add messages, what are the different functionalities of this. And what the state is, we define as the main baseline or the main foundation of the line graph on it. Okay, and in any of the node, a node takes in a state as what is the current state and does some operation and gives us the next state as what is the uh, next corresponding state to be. Okay, so because I said that the node takes in a state and gives output as a state, so here you can see like when we are defining a node, define my node, so what data type it takes is a state. Okay, and it also gives the output as a, it should be a state because the state is of a type dict or a dict, so it gives the output as a dict. Okay, we can define it as a state as well. And suppose say this node is doing nothing but invoking an LLM. That means we're calling an LLM, right? Suppose there is an LLM, OpenAI LLM. So this LLM is invoking with the input as a state messages. So for say the what is going into the node. Suppose there is a we are changing the state message as hi, this is Sabyasachi. Okay, so the state message would get updated to hi, this is Sabyasachi, and that would go into the node, and the LLM would get invoked as hi, this is Sabyasachi, and then it would wait for the output. So the output can be anything, like the output of the LLM invoke would be a output of the LLM only. So and then the output of the LLM would be a message type only, and that would override the state. Okay, so the state is something which goes like into a node and out to a node. And to define like how all of my nodes are connected, what we do is something, what we use is something called as edges. Okay, so there is something called as edge, like suppose there is a node A and there is a node B. Okay, and then we want to like post execution of node A, we want the execution of node B, right? Then we can connect it to a simple node, or we want like if A is node, like suppose say A is a calculator node. If the calculator node gives an answer which is say more than 100, or the sum of two numbers is more than 100, then it only should go to the node B. Then what we can use is something called as a conditional edge. Okay, so this conditional age function is also what I discussed with you earlier as well in the semantic routing as well. Suppose say there is a node which is a tool node, which is a calculator node, or there is a node which is something called as semantic or something like uh, a weather API call node, right? Based on conditional edges, that means because the lang graph in the definition we have explicitly defined that this is a node, it can do that it can call a weather API, and it can give the answer because it knows that then based on the condition it can call that particular node. Okay, so here like we want from node A, we want to traverse to the routing function. Suppose the routing function is something which is a main deciding block, that if the call is an API call, then it needs to go to the API. If the call is a tool call, it needs to go to the tool. Okay, that's how we define. So these are the main three defining blocks of the line graph: state, node, and edge. And the next comes the state graph. Okay, so this is mostly the builder with the state schema. So what the state graph does is it takes the state as an uh, state class, and it creates a state graph. And there are different components like register the node function. Like after compiling and building, we can add, like, compiling that, while building the particular graph we can add node. Suppose say I want to make a node A, so graph dot add node, and the name of the particular node, whatever node I want to give, say test node, or uh, any other node, or a tool calling node, anything, and what is the function of that. So whatever function I have defined, suppose this function I have defined my node, so name can be, say, test node, or anything can be given, and the function is the name of the function. And the add age. Suppose say I want to add age between A and B. So this is how I can add graph dot add age A and B. And if I want to add conditional edges, so graph add dot add conditional edges A and B. So these all are explicit to LangGraph. So these are there in the LangGraph. So I would suggest you to go through the documentation of LangGraph and understand as what are the different components which are available, through which you can build this all systems. Okay. And the other thing which is there is, like, for every graph to start, or for every lang graph to start, it needs to have a starting point and it needs to have a end point. Okay, so to define the start point, what we can do is we can define a node with the name of the graph dot set entry point. Okay, so this is the first node which you're running, and then graph dot builder. So this would compile into a runnable object, and graph.invoke, it would run synchronously. Graph.stream, so on the stream I would also come as how we can stream the outputs of the particular graph, as, like, say, stream the messages, so stream the state at each of the systems, at every node calling, what is the output of the every state at each of the node. Yeah, so reducers, I would suggest you to, once you pass on this particular document, I would suggest you to go through this and parallelly look up out there into the documentation of LangGraph as what are all of these particular functionalities which are there, and also why do we need to use the reducers. Okay, so that, like, what is the need of the reducers? Without reducers, what would happen as such? Yeah. So coming to the control flow. Yeah. So suppose say I want a direct linear execution. That means from if first the node A gets executed and then the node B gets executed. So directly I can add a normal edge, graph dot add edge A and B. So what it would do, from the first node A, it would go directly to the second node B. Okay. Suppose say I want to add some conditional edges and also some intelligence into it, that if the condition is this, or while the condition is this, then it would branch out, or if it needs to do certain kind of execution as such. So there is something called as branching. With what we can do is with the use of the conditional edges. Okay, and then suppose I want to, like, repeat it for a certain period of time. Suppose say for I want it to continue for 10 iterations, then I can write a for loops for I equal to for I, when it doesn't reaches 10, then till that point it would add a edge, and it would be pointing from B to A and A to B repeatedly. Okay, and this is mostly used in the case of the React, which I will come later in the reasoning and the acting kind of a scenario, what we leverage from the line graph. Or the retry function, suppose there is a retry functionality which is there. Suppose you have called the LLM and it has not given the answer, or the LLM is still streaming the output, then still, and we are keeping a monitor on the output as such. So it would be retrying on the state, and it would also be uh, giving us the output every time. And there is something called as a human in the loop. That means I want a human intervention whenever, like, the LM is giving an output, or whenever, like, any of the agent call is happening. And the others are the parallel fan out, like, if I want a single one to have multiple outputs, or vice versa. uh, and the other is a subgraph, like I want a graph within a uh, bigger graph. That can also be possible within the line graph as well. Yeah, coming to the main component of the usage of the line graph as such is the React agent loop. So mostly if you see in the lang chain, it was all sequential steps, like first do this and then do this and then do this and then do this. Like there was no reasoning component what we can attach over there. So here what we have incorporated is the React component or the React agent component. Okay, suppose I have this LLM. This is a start node. As I had already said, this is the start node and this is the end node. Okay, this is the two nodes what we have to explicitly define. And there is an agent call, like there is an LLM call which is happening. And based on the LLM call, it would decide that whether that needs to be tool call, or that whether that's need to be RAG call, or whether that's need to be a particular any loop exercise or whatever it needs to do. Okay, and then if it is a tool call, then we need to particularly call the tool node. Okay, as I had already defined, like we can define a tool node and let the LLM know with the something called as a function called as the bind tools. So with the bind tools, I need to explicitly define that these are the tools which are available in my system, and these are the individual definitions for that. Okay, like so there is a weather API tool, there is a calendar, there is a calculator tool, or say there is something else tool which is there, which is specific to my system. I need to specifically define those tools. Okay, so the agent would then call that particular tool, and then suppose I want to use the output of the tool. Suppose say I want to ask a question, right? How is the weather uh, going to be tomorrow in Bangalore? And if it is going to be good, and if the temperature is more than 25 degrees Celsius, and if it is not raining, I want to go for playing football. If I want to go for playing football, then suggest me some of the good uh, playing grounds near me. Okay, so I had given a set of prompts to the LLM or to my line graph system, and it needs to break down into individual things, and individually it needs to call the LLM, or whether to call the LLM, or whether to call the tools, or whether to call the invoking the RAG agent as such. So that is where the React agent comes into the picture. Okay. So if you remember, the first was like, how is the weather going to be tomorrow in Bangalore? So for that, because it knows that the first question is a weather API call, it needs to invoke the tool calls. Okay, because it knows that in the bind tools I have already given that there is something called as the weather API which is available. Okay, and then from that it would directly call the weather API, and then because the answer is yes, then it would go again to the LLM, and then it would give the answers for the other things, because it sees that yes, the weather is going to be good and the temperature is going to be more than 30 degrees 25 degrees Celsius. Because it is more than 25 degrees Celsius, and the other asks which are there, like what are the different fields which are available to play, then it would give me some of the suggestions based on the its own knowledge, or it can directly do a web search like a Bing search, or any of the search APIs it would directly call, and then it would give the answer along with the first answer it had taken. Okay, so what here you can see that it had done something called as a reasoning. Okay, it has done a reasoning on my first calls output, and also it has done a reasoning on these individual components what are there in my subsequent prompts as well. Okay, so like here you can define the routing function, like should continue, like if the last messages of the uh, set of messages whatever I'm passing, the state of the last message, if the last message is return tools, then it should end. Okay, this is how you can do, or human in loop also you can do over here. Yeah, for the interest of time, like I need to hurry it up given that we have got 3 more minutes. So uh yeah, so before going to persistence, let me tell you something, like because I think most of you would have used LLM as such, And if you ask like what, hi, this is Sabyasachi, and suggest me some of the good cafes near me. Okay, and it would suggest me some of the good cafes near me in the next answer. And next, whenever I ask like, hi chat, what was my name? In that case, it knows that my name was Sabyasachi. Okay, it doesn't say that I don't know your name. This usually happens in the chat GPT, the one which you use in the web portal, right? Or the Gemini call as such. Explicitly, if you call the OpenAI API or the Gemini API, like, hi, this is Sabyasachi, suggest me some of the good cafes, it would give me the set of the suggestion of the good cafes. Okay, but in that case, it won't give me the answer to my next question, which is, hi, what was my name? It would say that I don't know your name, because there was no memory as such. It doesn't know, it doesn't have any memory component in it. It never stores anything. It just, LLM, as I had already said, it just a next sequence or a next character prediction system. It does not know what is the memory as such. So that memory is different. How it retrieves those memory, how it knows the memory, and how it uses those memory, that is different. And this persistence is different. So try to separate both of this from each other. That uh, storing of the memory as like storing the conversation history is something different versus the persistence is something different. This is more towards usage of the line graph, wherein we are using some of the components of the line graph, so that whenever like we are executing the line graph, if in, say, any unforeseen situation happens, like say the line graph crashes, or we want to know like what was the state of the system when it had executed that particular prompt, then in that case we use this persistence thing. It has got no relation with those memory or the explicitly saving of the memory. Okay, hope this is clear. So yeah, so like there are different components how we can save those memory. So memory here, the reference is with the saving of the checkpoints. Okay, one is the memory saver, the other is the SQLite saver or the Postgres saver. So this is the mostly what we use in the production level system, wherein for uh, like for every checkpoint. So checkpoint, if you would think of, it's like, suppose you are playing a video game and you have done one step after another, one step after another, and suddenly your internet goes away, right? And whenever you reconnect to the internet, you again just respawn back at the same point where your internet went off, right? Or you got like you're playing some system and you uh, unfortunately you lost your life at a certain point, and for respawning it knows that there was certain checkpoint from where you need to respawn, right? Those are the checkpoints. So these are the checkpoints which are generally used for us to keep a track of as how the our line graph was performing, and to keep a track of the states as in that particular state. So what was the LLM call, and what was the sequence of steps which had happened at that particular checkpoint. Okay, and also there is something called as a thread ID. Suppose say you and your friend both are chatting with the chat GPT, and how does it know that you are different from the other? So what it creates is like a session for you. So the session for a user A is different from a session for the user B. And for every session, for every chat, there is a thread ID. And for every thread ID, it's a unique identifier through which it knows that yes, what has happened for that particular session for this particular user. And through that also, using the line graph, we can still trace back and still we can get to know as what has happened. Okay, and there is something called as a time travel. So this is another component through which we can go back into the system and get to know as what had happened at that point of time. So because we had saved this particular checkpoints into some kind of a Postgres server, like a memory saver, we know that this is what has happened and this is what was the state at that point of time. And for debugging or for any kind of a prototyping or developing, we can use this particular thing. The last is the multi-agent architecture. So like I will give you a basic overview of this, not like going much into the detail. So whatever I had told you previously is a single agent system. Like this is a single agent system. It's a one single agent which does a tool call, which generates the answer, which generates the answer from the RAG, which does everything within a single agent. So this is a single agent system. What How can I leverage the land graph to have multiple agents? You can also say that with the use of the subgraphs. Yes, so we can use that over here as well. So there are different ways through which we can like orchestrate this multi-agent pattern. So like suppose this is my start node and this is the end node, and I have something called as a supervisor, which does a supervision of all of the worker nodes. And based on all of the worker nodes output, it gives say binary feedback that yes, whether the task is done or not done. Then the supervisor node would take a call that yes, all of the tasks are done, and then that would give a signal that yes, the particular graph execution has done, right? And the other can be like a we have one top supervisor and multiple sub supervisors. So multiple sub supervisors are doing sub interventions into the sub workers which are there. Okay, and each of the supervisors would be having individual agents into each. This is the best kind of a scenario where we have multiple agents and we want our tasks to be done parallelly uh, across all of the agents, because we have our LLM tokens available. We have our all of the RAG system or tools and everything which are available. So why not to use them parallelly, so that all of our tasks get executed in parallel fashion and also get it done in our stipulated time. Okay, and this is the sequential pipeline. So this is what I had already showed you, like, but the sequence of the patterns can also be one agent would be dependent on the other agent as such. And this is a parallel fan out which I was earlier discussing with you. So the last component of this is the streaming. So how do I want to stream the output of the particular LLM? Because like whenever we call the LLM is just giving one character at a time. So the streaming, the like whether we want all of the values to be provided or all of the updates, like for any of the states which is updating, if we want to debug the system or to monitor the system, we can use the update as the streaming mode over here. So here you can see graph to stream. How we are streaming is like, if you want the updates only, it would just give us the updates like concise, like this node has executed, that node has executed, this edge had executed as such. And if you want only the messages, then the stream mode is equal to messages, right? It would give me as and when, like, the LLM is giving me the answer like hi, the hi Sabyasachi, so hi space Sabya, each and every component would be coming one step at a time. Or like if we want the stream mode to be debug, then we can keep it debug, wherein it will give a multiple different other outputs which are intended for me to debug individual nodes and individual components. Okay, so this was most of the things on the high level I have talked to you. I would still suggest you to, like, in this next week, you would like you will be getting all the handouts on the different components and the different parts which are there. And I would suggest you to go through that and also get a detailed understanding and get hands-on into this, so that you get to know as how this works and how to add a node, where to add a node, where to add a conditional edge, where to add a normal edge, where to add a loop, or where not to add a loop. So these all things will come much more handy to you. Okay, thank you for your time. And if you have any questions, just do post that on the uh, comment box. I'll be happy to answer that. If not, then do pass it on to the host, then I can let you know offline as well.
Thank you, sir, for the amazing session. So yeah, everyone, this was all about the session. Now we are going to end the live stream. You can post your questions in the Discord also. We will answer them or forward them to sir. Thank you everyone for joining the stream. Thank you, sir.
Thank you so much. Thank you. Have a good day. Bye.